Hello, my name is Ashley Peake, and this summer I've had the chance to work as a Robotics Institute Summer Scholar in the Air Lab at Carnegie Mellon. This summer, my project has been model-based reinforcement learning for off-road driving. So in an autonomous off-road driving task, a vehicle must navigate unknown and dynamic environments, often without roads or predefined traffic patterns. Autonomous off-road driving is important for applications in search and rescue and ground exploration, among many other things. These time-sensitive and potentially dangerous tasks make autonomous vehicles a particularly beneficial option to employ. It is thus critical to develop intelligent, efficient, and safe planning algorithms for unmanned ground vehicles. Autonomous off-road driving is a particularly challenging task because vehicles must be able to navigate within clustered and dynamic environments and interact with various obstacles. Because the dynamics properties of the environment are critical for successful navigation, semantic and geometric features alone are insufficient for planning. However, explicitly modeling the dynamics is difficult due to the size and complexity of such environments. Previous work often relies on simplified physics models of the environment or attempts to learn a policy directly from the environment without ever exploiting the dynamics. These approaches face difficulties in terms of accuracy, robustness, and generalized performance. So we attempt to address these issues by proposing a model-based reinforcement learning approach for off-road driving. Broadly, model-based reinforcement learning is a self-supervised method that involves first learning a dynamics model of the environment. So this model is trained using experience collected from the environment by allowing our robot or our agent to interact with it. And so we use this model to predict how the environment would respond to any action that we take. From here, we can use traditional planning algorithms to select what the best action actually is. So for our specific approach, we're going to train a model that looks something like this to predict aspects of our state that are most relevant to planning. And so specifically, these are the dynamics. In other words, what's going to happen in the environment after taking some specific action. The value, which is just how good of a position we're currently in relative to our end goal. And then the policy, which is what action do we expect our agent to take next. From here, we can use a Monte Carlo Tree Search as our method to select the best actions. And this overall builds from the MuZero framework recently proposed by Google DeepMind. And so the important thing to take away here is that Monte Carlo Tree Search requires looking into the future to see what will happen if we take different actions. In the off-road driving task, as I said before, we do not know the dynamics ahead of time, so we can't actually use this kind of method by itself. By first learning the dynamics model I just showed, we are able to incorporate the dynamics information into our planning to actually use this efficient kind of approach to ultimately optimize our actions. In preliminary experiments, we have tested this approach on the Lunar Lander OpenAI gym environment. So in this task, a robot must land in a specified zone, as shown in this figure here. While this scenario diverges from our ultimate off-road driving application, it's a toy example that allows us to model control parameters for a robotic vehicle. And in this way, it provides a baseline for discussion for our larger problem. In this case, positive reward represents solving the game correctly, or landing within this yellow zone. You can see in training performance that we are able to reach this threshold. However, the maximum reward is 200, and we never even get close to that. And you see that the purple robot, in an example of testing performance, does land correctly in this zone, but it does not take the most efficient path, which would just be coming directly down. And so this is something to note and address as we move forward with complete testing. But because this was relatively quickly, simply, and efficiently able to solve this game, we can still move forward with this as a promising approach for our off-road driving problem. In the future, the first task is to complete full experiments in a PyBullet simulation designed to test off-road driving. It's going to look something like this. As I just mentioned, we also need to alter model architecture and some training procedure so that we can actually find the best path. We also eventually plan to test this method in physical experiments as well as incorporate model uncertainty. Ultimately, this work can be used in applications like search and rescue and ground application, and it's critical that algorithms for such applications be both safe and efficient, further motivating the development of our approach. So that's all I have for now. I would like to thank my sponsors and mentors for their support throughout the summer. This project could not have happened without them. And thank you for watching.